Hello, in this video, it's going to be the third video in our air-breathing propulsion device engine series. And with this one, we're going to talk about turbofans. And the first one we talked about turbojets. First one we talked about ramjets, second one we talked about turbojets. Now this one we're going to talk about turbofan engines. Now turbojet and turbofan engines are very similar in how they operate, but there's one key difference. A turbofan, the casing of the engine is much larger than the core of the engine right here. This is the core. Now there's this casing, and then there's a fan, that fan right here that covers the entire diameter of that larger outside of the engine, and then air can pass through this section around the core of the engine, or it can pass through the air can pass through the core. Now that's differentiated by this thing called the bypass ratio, which is the air passing through the fan compared to the air passing through the core of the engine. So this would be the air passing the fan, this would be the air going into the core. And now these can be numbers anywhere from, I guess it can be a 1-to-1 ratio, but they can be, 5, 6, 7, 8, 9, 10, anywhere up in those ranges or even higher, depending on the engine. So engines that use more jet thrust, so this is the jet thrust right here. So the more jet thrust compared to the fan thrust, that would be a low bypass ratio. So that means more air is going into more air is still going through the fan, a mass flow rate compared to the core, but it's still low compared to a high bypass ratio. So a high would then be anywhere between, I would say, greater than 8, to 10, but it doesn't really matter with, there's no calculations that this is a low bypass, this is a high bypass. But so commercial and large transport aircrafts usually are using high bypass engines, while military fighters are usually using low bypass engines. So, and also low bypass engines may also have an afterburner. So a commercial, so the more bypass ratio you use, the more efficient it's going to be at lower speeds, and then the higher speeds that the engine or the plane wants to travel, usually the lower bypass ratio it is going to use. Because there's a key difference here. Turbofans are efficient at medium speeds, so anywhere between a propeller and a turbojet. So it can be about 310 to 620 miles per hour. So about in that range, 500 kilometers per hour to about 1,000 kilometers per hour. And you can kind of see with the turbofan, it kind of combines propellers and your turbojet. So it's kind of somewhere in the middle. And that's why it gives you that efficiency somewhere in the middle. So you can look at here's a kind of a phase diagram where you can see kind of all the different spots. So we have the inlet, diffuser. Now we have for the outside fan part, we have this compressor and then a nozzle and then the exhaust. But if the air then is going through the turbojet part, we have a compressor, combustion chamber, turbine, and then if it goes through, so if it had no afterburner, there would be a nozzle right here, and then that would be it. But this represents an afterburner, has a flame holder, a burner, then nozzles, and then exhaust out the back. So as you can see also that right here. Fan, diffuser, compressor, combustion chamber, and then nozzle. So sometimes, another part of turbofan engines, sometimes they will mix the exhaust gas and the gas, or the exhaust gas. They would mix the exhaust gases coming from both of these, and that will lower the average temperature of the exhaust gas. So if you were in a situation where you wanted a low temperature signature, if you're in a fighter jet, something like that, you can mix the gases, the exhaust gases, to lower the average temperature, because the exhaust, and we'll see this when we do a calculation, the exhaust temperature coming out of the fan is obviously going to be a lot lower than what is coming out of the combustion chamber. So you can mix those, and theoretically it does give you more performance. So now we're going to do an example problem where we analyze every single step, find the pressures, find the temperatures, and then find the overall efficiency of a given turbojet engine. All right, for this turbofan engine, we have all of our properties here. So it's going at a Mach number of 0.82. The compression ratio of the compressor, or the pressure ratio of the compressor, is 14.0. The pressure ratio of the compressor for the fan out here is 2.25. The bypass ratio is 5. The specific heat constant, or specific heat ratio for the cold air is 1.4, or compressor. Specific heat ratio for the turbine area, 1.3. Specific heat ratio for the afterburner, 1.2. Gas constant for air, 287. The atmospheric temperature, 240 Kelvin. The pressure in the atmosphere that we're working with here, 80 kilopascals. Plyotropic efficiency for the compressor is 0.81. Compressor for the fan, 0.84. Plyotropic efficiency for the turbine, 0.9. Efficiency for the nozzle, 0.99. Nozzle, fan nozzle, 0.98. Diffuser efficiency, 0.98. And then pressure ratio for burner, efficiency of the burner. PIS, not sure what that is. The pressure ratio for the afterburner is 0.95. And then the efficiency for the afterburner is 0.99. The temperature ratio of between the state 4 and versus TA is 6.5. And then the ratio between state 7 and the atmosphere is 8.5. So let's start with our inlets. Buckle up. It's going to be a long question. TO1. Let's calculate the total temperature at state 1. So this is just after as the air comes in. Use this equation right here. So we expect the temperature to increase, and it does. That'll be 278.28 Kelvin. And then we can find the pressure. And we're using the gamma C here because the air is still cold, relatively. So the pressure also increases. So which makes sense given our ideal gas law that as pressure increases, the temperature will also increase. And then we can also say that TO2, temperature at state 2, equals temperature at state 1. Now we're into the diffuser. We have PO2 equals the pressure ratio of the diffuser. And that makes sense. And now, but we don't have pi d, so we don't have our pressure ratio of the diffuser. We can use our formula. So there's our pressure ratio for the diffuser, and we have our cold temperatures, 0.9917. Therefore, PO2 equals 123,387.45 pascals. So the pressure does not drop all that much as it's going through the diffuser. Now we're going to look at the fan states. So this will be states 2 to 11. So we are now bypassing the engine core. So we have this equation right here. We know this. So the pressure will increase as it's going through the fan because it's getting compressed by the fan that is spun by the turbine. So increases by 2.5 to that pressure. We have the efficiency of the compressor. and this is raised to that value. Then all of that minus 1 over pi c prime polyotropic efficiency, and then this is raised to this. The efficiency of the compressor and the fan, 0.8209. Now, I want to look at, I want to solve for the temperature ratio. And this is raised to this value right here. All that minus 1 divided by, and then this is all plus 1 right here. That equals 1.318. So we can calculate now the temperature at state 10 equals tau C prime times TO2, which equals 358.76 Kelvin. So it makes sense, as going through the compressor, temperature increases and the pressure increases. Now if we want the temperature at the exit, which is temperature at state 11, use this equation. And again, this is all still the cold temperature states. And then this would be 253.575 Kelvin. So as it goes to the fan, increases in temperature, increases in pressure. But as it goes from state 10 to 11, or the exit temperature, it drops back down in temperature, which makes sense. All right, so now we're going to quickly calculate the thermo properties for all these. So we want the CP for cold. These are the specific heat capacities. So as you can see, as the specific ratio decreases, the specific heat capacity increases. All right, so now we can calculate our exit velocity. Using this equation right here, and then that will give us an exit velocity of 459.69 meters per second. And that doesn't mean much, but let's quickly calculate what the velocity at A is, which would be MA times AA, so which would be Mach number times the square root of gamma cold R times TA for your compressor. And this would be 254.64 meters per second. So, given these properties that I outlined in this question, the velocity of the air increases quite a bit as it goes through the fan. But now we're going to calculate all the stages for the air now going through the jet part. So this is all very similar to the turbojet engine. So if I don't say something in this video, maybe because I said it in the last one, but it's all very similar. So we can calculate the pressure at 3, and this will increase a ton. So you get that much pressure. So pressure increased a lot. Now we want to find the efficiency of the compressor. And this is a non-ideal turbofan engine, if I didn't make that clear. So this is raised to this. It's kind of hard to show, make it look like it's raised, but. So this is EC minus 1, that would equal 0.7324. So not a great efficiency there. Now we can find the temperature ratio of the compressor. this is all plus that. And you get 2.537. So calculate our TO3 equals tau C times TO2, which equals 690.71 Kelvin. Which makes sense, okay? So we got the air, goes through the compressor, heats up, and the pressure increases. Ideal gas law, that makes a lot of sense. All right, so now we are at the main burner. So this is states 3, 2, 4. Into the combustion chamber we go. Calculate the temperature at 4. This is a very hot temperature. Now, if this engine didn't have an afterburner, this would be the max temperature. But the pressure does drop a little bit from the compressor. Now we can also calculate our fuel for the burner, our fuel to air ratio. Now I am skipping over plugging all these numbers in to save time, but we also have everything, every variable that I'm kind of skipping over plugging in because we already calculated it. So that's our fuel to air ratio. Pretty low, pretty reasonable. Now we get into the turbine states. Should be 4 to 5. So our temperature ratio for the turbine, so quite a large equation. We get 1 minus then. There's our efficiency right there. And this is equal to 0.568. So our temperature at state 5 equals tau T times TO4, 886.2 Kelvin. So temperature drops pretty significantly as it goes to the turbine. Now the pressure is really going to drop here. Oops, I don't want to write that. So we'll find a pressure ratio for the turbine equals tau T to gamma T divided by the polyotropic efficiency of the turbine. And now we're dealing with this new specific heat, or the specific heat ratio value, because now the air is significantly hotter, so the properties change. So now we're using our gamma T, which is 1.3. Now the pressure is going to drop a lot as it goes to the turbine. So pretty much it dropped from, 1,700,000 pascals to all the way down to 100,000 pascals. So quite a significant drop. But we're not done yet, because now we have an afterburner. So if there was no afterburner, you could use this temperature to calculate this temperature and this pressure to calculate the exit velocity. But because we have an afterburner, we have to continue on. So our state 7. So now our temperature goes way back up. But our pressure continues to decrease. Now we're going to calculate our fuel to air ratio, the afterburner, which is going to be very high. We also include our fuel to air ratio of our first burner. have our heat of combustion right there. S equals 0.0613. So you can see the fuel to air ratio of the afterburner is way higher than the fuel to air ratio of the normal burner. That's pretty interesting. So now we got our nozzle states. 7 to 9. Whoops. We have new properties now for our air. And that would equal 1958.76 Kelvin. So that is very hot air as it goes to the afterburner. So that's why I don't even know if you can mix gases through an afterburner, but that gives you a big heat signature for any like heat-seeking missiles. And the velocity of the exit velocity is not as high as you would think, unfortunately, because there's just not a large temperature drop between the temperature in the afterburner and the temperature coming out of the nozzle. The air is still faster than coming out of the fan, but not as fast as you would maybe think so. And the Mach number is quite slow because we calculate the speed of sound at the exit, 821.33 meters per second, which gives you a Mach number at the exit of 0.644. So the afterburner is really not efficient for this engine. But we can find the overall efficiency for the engine if we keep on going here. Almost done. So we got R. It's quantity R, which is VA over VE, which equals 0.4814. Oh, let me go back here real quick. So if there was no afterburner for the nozzle states, so you would use TO5 in here, and then you would use TO5 right here. And that would give you, if there was no afterburner, you would skip over this section. And we got our prime value, which equals VA divided by VE prime. So that's the exit velocity of the fan, exit velocity through the core of the engine. Calculate our total fuel to air ratio, which is F3 plus, which equals a whopping 0.0915. Calculate our impulse for the specific thrust. That's equals 224.66 Newton seconds per kilogram. Now we can find our thrust specific fuel consumption. Uh, 6.788 times 10 to the negative fifth kilograms per Newton seconds. Can also be written as 244.37 kilograms per kilonewton hour. Now I can find the thermal efficiency through this large equation. We got our thermal efficiency of 0.116. That is very low. We have our propulsive efficiency through this equation. And that equals 0.6986, so much higher, but alas, our overall efficiency is only a meager 0.0813, so not very high. But going through all these calculations, what did I really want you to see is going through these calculations is good because you can see how the pressure and temperature is affected at each state of our process. So we can review it one more time. So as the air is coming through from the atmosphere, pressure increases to state 1, temperature increases. As it goes through the diffuser, the pressure drops, but temperature stays the same. And yeah, the pressure drops just a little as it goes through the diffuser. So when it goes to the fan, because the fan up here is attached to a compressor, the temperature increases, pressure increases, and then as it accelerates through the nozzle, pressure decreases and temperature increases as it goes through the compressor here. Pressure increases, temperature increases, combustion chamber, pressure decreases, temperature increases, goes to the turbine, pressure decreases a lot, temperature still decreases. As it goes through the afterburner, temperature increases again, pressure increases, and then temperature and pressure go down as the gas then goes through the nozzle. So those are the basics of a turbofan engine. If you made it through this video, I'm impressed. So that's about all you need to know. They're pretty simple, but also very complicated.